Greetings, we are the SJC Gators from San Jacinto College. Our Texas Space Grant Consortium Design Challenge is to create a solar concentrator for extraterrestrial use. The SJC Gators is made up of 4 team members, Damian Leos, John Burback, Ian Ebert, and myself, Michael Kruger. Our faculty advisor is Dr. Nathaniel Wiggins. We have 2 mentors, Mr. Christopher Mendel and Mr. Houston Green. Typically, solar concentrators are designed using either lenses or mirrors to collect and to focus the sunlight. Concentrated solar flux has both thermal and electrical uses. One design option is the parabolic mirror, which has a really high concentration, but the problem we've encountered in the past is that it requires tracking of the sun. So as the sun moves, that mirror has to track it. Fresnel lenses, on the other hand, have a really wide acceptance angle and therefore show great promise if we wanted to eliminate that solar tracking. So why should we put a solar concentrator on the surface of the moon? Well, we could use it to provide energy and lighting for a possible human habitat. We could also use it to melt lunar regolith, which is basically the topsoil of the moon. Within that lunar regolith are valuable elements. There's oxygen, which we could use for the human habitat, and there's also helium-3. Helium-3 has great potential to provide energy. In fact, 44 tons of it is enough to power the United States for an entire year. And it's estimated that there's around 1 million tons of helium-3 on the moon's surface. Designing a solar concentrator for use on the moon comes with its own unique challenges, such as lunar dust. Lunar dust is composed of very small, sharp particles that float around on the moon's surface, and they stick to almost everything. This causes problems for machines that have moving parts because the dust gets inside of those joints and causes them to seize up and to degrade. It also collects on optical surfaces and blocks the light, which is a huge problem for solar concentrators. The temperature on the surface of the moon cycles from 100 to 400 Kelvin. This large variance in temperature can cause materials to crack and deform. Therefore, our lunar solar concentrator must meet the following objectives. It needs to have a wide angle of acceptance to remove the need for tracking and moving parts. It must be able to generate enough heat to melt lunar regolith and endure the large changes of temperature on the moon's surface. It will need to be durable to survive a launch, possible contact with lunar dust, and possible meteorite collisions. A low density is also important to keep costs down, and the optical surfaces will need to be kept free from lunar dust accumulation. On the left, you can see the original design inspired by our mentor, Mr. Christopher Mendel, and on the right is our newest design with several improvements. Our concept involves a combination of lenses and mirrors. On the outside are 2 parabolic mirrors, which direct light onto a cylindrical Fresnel lens. The Fresnel lens then focuses the light onto the rounded edge of a funnel receiver lens, which then redirects the light onto a fiber optic cable.
All right, so I'm going to give you guys a rundown of our Fresnel lens model that we designed. Basically, what a Fresnel lens is it reduces spherical aberration. And spherical aberration is light's error in its ability to focus onto a single point. So you'll experience a spread of light as opposed to just light focused onto a single point. What we did to design this was we used a mathematical program called Mathematica, and we designed a 2-dimensional model in there using coding and formulas. You can see on the upper right-hand corner where we translate this spherical lens into the Fresnel lens along axis lines, and you can see where the ribs were created along those lines. We took this 2-dimensional model to make our 3D model using this concept, and we rotated the model and the sketch around an axis. This allows us to capture light in 360 degrees as the sun rotates in the atmosphere of wherever this will be placed. In our 3-dimensional model on the lower right-hand corner, you can't see the individual ribs in the model because there are 286 of them. The fact that there's 286 ribs allows us to focus the light to a more precise accuracy, and it also allows us to reduce the weight of the lens by making the lens thinner.
I will be presenting the funnel lens. The edge of the funnel lens is placed at the focal arc of the Fresnel lens so as to maximize the amount of light captured. The bottom leftmost photo shows the highlighted area where the light would be directed. It uses internal reflection to redirect and focus the light down the narrow end of the tube, which will head off into a fiber optic cable. On this slide, you can see a hand-drawn ray trace of light entering and reflecting within the funnel. At the top right, you can also see the light entering into the funnel at a wide range of angles. You can also see how the light bends once it enters into the funnel. This is due to Snell's law and the refractive index of aluminum oxynitride. Aluminum oxynitride is the material that we chose to go with for both of our lenses. The critical angle of aluminum oxynitride is 33.9 degrees, and due to the phenomenon known as total internal reflection, any ray that hits at an angle of incidence greater than 33.9 degrees will reflect within the funnel. Of the 9 rays that were hand-drawn, only 1 escaped out of the funnel. The other 8 were successfully contained and redirected throughout it. On this slide, you can see the materials that we researched for our lenses. Aluminum oxynitride, also known as Alon, as shown on the top row, had the highest Knoop hardness, which makes it the most scratch-resistant and most durable on this list. The CTE, or coefficient of thermal expansion, is also relatively low, which means it's able to withstand the fluctuating temperatures of the lunar surface. The melting point is also way above what is needed to melt regolith, which is at 1775 Kelvin.
The mirrors will have a parabolic shape with their focus on the edge of the Fresnel lens. After examining many materials, graphite epoxy stands out as a great option. It has a low coefficient of thermal expansion and a very high tensile strength, which means that it is durable. It is also a great economic choice due to its low density and cost.
When we designed the base, we decided to use a honeycomb structure. This kind of structure helps to minimize the amount of needed materials while also maintaining structural integrity for prolonged use in extraterrestrial environments. Another feature is the optical mounts that provide easy access to the lenses in the event of repair or replacement. We selected aluminum for the structural component of the project due to its low cost of production, low density, high tensile strength, and high melting point.
We've done a lot of research into the optimization of our fiber optic cable design. Recent research has shown the benefits of hollowing out the fiber optic cable and replacing the inside with silica fiber cords. This is beneficial because it reduces the energy loss of light energy into thermal energy with the reduction of mass inside the cable. These silica fiber cores will be shaped in a kagome or hexagonal lattice structure, as you can see on the bottom right-hand corner. This structure is important because it reduces light energy loss throughout the cable because of the high incident angles. The cores can also be filled with compressed gas to actually amplify the light being transmitted throughout the cable, as recent tests have shown. With the continuation of our project, we have a few areas that we would like to focus on in the future. First being our fiber optics materials for the insulation and interior of the cable. We'd like to run simulations to prove the efficiency of our optics. We'd also like to optimize our base design, meaning possibly changing the material and the interior design of our base. This would also include modifying the fasteners and improving them to hold our optics in place and hold our structure in place in extraterrestrial habitats. We'd like to look at lunar dust solutions. One possible solution that we looked into was actually creating a positively charged electric field on the optics and using that to repel the positively charged lunar dust particles.
We'd like to give special thanks to our mentors, Mr. Christopher Mendel and Mr. Houston Green, and to our faculty advisor, Dr. Nathaniel Wiggins, and to the Texas Space Grant Consortium for giving us this opportunity, and of course to San Jacinto College.